The Ballast Water Management (BWM) Convention aims to protect the environment from the potentially harmful effects of ballast water discharges. This film describes the requirements for record keeping and the options for exchange methods and treatment methods. The Ballast Water Management Convention identifies 4 different methods to achieve the aims of the Convention: ballast water exchange, ballast water treatment, ballast water isolation, and sediment management. A ship-specific ballast water management plan that describes which methods are used and how compliance is achieved must be developed. G4. Guidelines for ballast water management and development of ballast water management plans. Contains detailed advice on ballast water management, recording procedures, and content of the ballast water management plan. All ships must have a ballast water record book. The record book must show records of ballast taken on board, ballast circulated or treated, ballast discharged into the sea, ballast discharged into reception facilities, and ballast discharged accidentally or under exceptional circumstances. The book may be electronic or paper. Every entry must be signed by the Ballast Water Management Officer and every page signed by the master. The record book must be kept on board for 2 years from the last date of entry, then maintained by the company for a minimum of 3 years. There are minimum content requirements, which are stated in Appendix 2 to the Annex. Most port states require numerous reports to be submitted in advance of an arrival in their territorial waters, or even in the exclusive economic zone. These borders are depicted in the nautical chart. This includes reports on ballast water management activities. IMO has developed a standard reporting form, but national rules also exist. Check with the port state what their rules are. Note that the USCG has issued rules with penalty provisions if a report is not submitted. The ship owner has a number of ballast water management methods to choose between. A combination of methods can also be used. Depending on the trading area, the age of the ship, and the planned maintenance cycle, ballast water exchange may not be sufficient on its own. Careful consideration of the methods is necessary, and the choices should be documented in the ship's ballast water management plan. The G6 Guidelines for Ballast Water Exchange describes 3 different main methods for ballast water exchange: sequential method, flow-through method, of which the natural exchange method can be considered a special case, and dilution method. Each method has advantages and disadvantages. The G6 guidelines provide detailed advice on safety precautions to be observed during the exchange. A ballast tank is first emptied and then refilled with replacement ballast water to achieve at least a 95% volumetric exchange. Replacement ballast water is pumped into a ballast tank, allowing water to flow through overflow or other arrangements. This means that the tank may be subjected to higher pressures than normal. Natural exchange can be considered a special case of the flow-through method, but without using pumps. Water enters through an opening in the forward end, is led into the tanks, and exits at the aft end. This method is limited to tanks below the waterline. Replacement ballast water is filled through the top of the ballast tank, with simultaneous discharge from the bottom at the same flow rate and maintaining a constant level in the tank. When the sequential or flow-through methods are used, particular attention must be on stability and stresses on the hull. These methods require the removal of large quantities of water, and at sea the static and dynamic forces working on the hull must be calculated carefully. Uneven load distribution causes shear forces and bending moments to act on the hull, and the movement through waves adds torsional forces, particularly on long ships. The dynamic forces working on the ship at sea requires careful calculation of bending and shearing forces to ensure they stay within allowable limits throughout the exchange process. We have considered the requirements for the Ballast Water Management Plan, Ballast Water Record Book, Ballast Water Reporting and Ballast Water Exchange. There are a wide variety of treatment options for ballast water. We shall briefly consider the main treatment technology options. The main technologies utilized in ballast water treatment systems are electrolysis treatment, ultraviolet treatment, ozonation treatment, and chemical injection. Most of these technologies are supplemented by filtration, either classical static filtration or dynamic filtration. Each technology has advantages and disadvantages. In an electrolysis system, an oxidizing disinfectant can be produced in a process known as water activation. An electric current is applied to water in an electrolysis chamber. The water is broken down into an acidic biocide known as analyte and an alkaline substance known as catholyte. The analyte is injected into the ballast water, where it creates oxidizing chemicals which kill the unwanted organisms. The catholyte can be used to neutralize the pH change later, so preventing excessive tank corrosion or environmental harm. Besides analyte and catholyte, electrolysis can produce hydrogen gas, which must be handled on board the ship. The amount of active substance generated is dependent on the salinity level of the water. The oxidation reaction of seawater is also temperature dependent. The reaction does not create the disinfectant at effective levels below approximately 15 degrees Celsius. The water must be heated, hence the higher energy consumption. The IMO Convention stipulates a limit of remaining disinfectants for the outgoing ballast water. It may therefore be necessary to neutralize harmful byproducts prior to release, should the IMO limit be exceeded. UV systems generally use filters and ultraviolet light. UV light kills or inactivates organisms by disrupting their DNA, leaving them unable to perform vital cellular functions. The efficiency of systems using UV light depends on total suspended solids, TSS, and the opacity of the water, in other words, how cloudy it is. High levels of TSS or color will cause a decrease in the UV transmittance level. Consequently, the UV intensity will have to be increased, resulting in an increase in power consumption and a considerable decrease in lamp life. If the water cannot transmit the UV light, then the UV cannot disinfect efficiently, because the organisms may be shielded from the UV light. A filter is advantageous in waters with high levels of particulate and organic matter, as a large proportion of organisms will be filtered out before processing. Filters which automatically backflush when a certain pressure drop is exceeded may reduce the flow rate and increase the energy consumption in water with high sediment content. UV systems do not form any harmful byproducts, and the process itself is largely independent of the temperature and salinity, although UV transmittance is not. The process may have relatively high energy demand in such cases. Chemical injection systems are often used in combination with filtration. A chemical solution is injected into the ballast water to ensure disinfection. The disinfectant may be liquid or granular and is often similar to the disinfectant used in domestic water treatment plants. Chemicals may successfully treat ballast water under various conditions and are not affected by salinity of the ballast water. Some systems require neutralization prior to discharge. Chemicals used are trademarked and supply might be limited to specific ports. The chemicals must be stored on board in closed containers and are highly toxic. The use of chemicals requires implementation of strict safety provisions and crew training. Recharge, however, is often done by the supplier. Due to the need for chemicals, chemical injection systems may have higher operational costs than other systems using other technologies. Holding time may be affected by temperature. The efficiency of chemical processes depends on many factors, including temperature. Chemical reactions are usually slower in colder water. Ozonation systems generate ozone, O3, from ambient air. Ozone is injected into the incoming ballast water to oxidize and neutralize aquatic species. Ozone reacts with other chemicals that occur naturally in seawater to form hypobromous acid and hypobromine ion. These are effective disinfectants. Where ships take on fresh water as ballast, for example ports located in lakes or rivers, brominated compounds are not formed and the ozone alone acts as disinfectant. Waters with high particulate and organic matter require higher doses of ozone to ensure sufficient disinfection. Salinity and temperature are not obvious factors affecting the efficiency of ballast water treatment systems employing ozonation. However, longer holding time may be required. Both ozone and hypobromous acid disintegrate extremely rapidly. Ozone disintegrates significantly slower in fresh water than in seawater. Residual byproducts are measured according to IMO acceptable limits and neutralized prior to release. Ozone is known to induce breakdown of tank coatings and accelerate corrosion. Since ozone is toxic, additional safety measures and crew training are necessary. Ultrasonic energy is used to produce high-energy ultrasound to kill the cells of the organisms in ballast water. Such high-pressure ballast water cavitation techniques are generally used in combination with other technologies. Ballast water treatment systems may combine cavitation with filtration, UV, ozone, or deoxygenation. Deoxygenation may be used in combination with other technologies such as cavitation or pasteurization. This treatment method involves stripping the oxygen from the ballast water to suffocate organisms. This is usually done by injecting nitrogen or another inert gas into the ballast water. The low oxygen level then kills most of the oxygen-dependent organisms. It generally takes several days for the inert gas to fully deoxygenate the water. If a ship is already installed with an inert gas system, then a deoxygenation system will not require more space on board ships. Deoxygenation can be used in combination with pasteurization, where the ballast water is heated to reach a temperature that will kill the organisms. A separate heating system can be used to heat the ballast water in the tanks, or the ballast water can be used to cool the ship's engine, thus disinfecting the organisms with the heat taken from the engine. Active substances used to kill unwanted organisms may also be harmful to the crew and the environment. The risks in storing and using the substances must be assessed with respect to the crew and environment, and always in accordance with the manufacturer's instructions. A byproduct of electrolysis is hydrogen, which is explosive when mixed with air. The hydrogen must be controlled to avoid creating an explosive atmosphere. A ballast water management system intended for compliance with the D2 performance standard must be of a type approved by IMO. This is done in a similar way to other types of equipment mandated for use on board a ship. The G8 Guidelines for Approval of Ballast Water Management Systems describes the process manufacturers must go through in order to obtain type approval. The USCG has its own regulations for ballast water management, and the United States has not yet adopted the Ballast Water Management Convention. The USCG discharge standard is similar to the IMO D2 performance standard for discharged ballast water. However, the regulations for type approval are more stringent than the IMO G8 guidelines. A ballast water management system used in ballast water discharge in US waters must have USCG type approval. The Ballast Water Management Convention has been ratified and the entry into force date is known. Putting the various deadlines together shows that 2022 is the latest possible date for full compliance with IMO and USCG ballast water performance standards. This is provided that all options for applying for USCG extensions and the timing of the IOPP certificate renewal are allowed for. We have considered a number of treatment technologies and regulations for type approval under IMO guidelines and USCG regulations.